mucho esfuerzo para tener aquí a distinguida profesora y visitante. Y pues bueno, le dejo la palabra para que me la presente.
Muchas gracias. Esto va por los estudiantes. Yo he oído a muchos de ustedes cuando saben que van a conocer a alguien que ven en los libros o en los artículos que han leído diciendo ¡wow! ¡Qué famoso! ¿No? ¡Qué bien! ¿Puedo ir a tomar un autógrafo? Bueno, ese fue mi sentimiento cuando yo conocí a Sandra Faber. Cuando yo era estudiante de astronomía, de maestría, la clase de galaxias la dio Roberto Terlenes. Así que somos generaciones, estamos ligadas en el tiempo, aquellos que están en astrofísica, ¿no? Y entre muchos de los resultados que vinieron en esas clases de galaxias, por supuesto, estaban las relaciones de escala, que entonces el grupo en el cual Roberto colaboraba, los 7 samuráis, estaban trabajando en esas relaciones de escala. Una de las primeras relaciones de escala, como saben, es la relación Faber-Jackson. Así que después, mucho tiempo después, realmente después de doctorarme, casi 10 años después, llegué a conocer a Sandra Faber. Entonces, cada vez que oigo esa excitación de los estudiantes que van a conocer a alguien que han leído algo sobre su trabajo, me recuerdo que yo también sentía esa excitación cuando era un estudiante, ¿no? Les voy a leer un poquito la semblanza, resumida, muy resumida porque realmente es extensísima, de Sandy. Sandra Moore Faber es una destacada astrofísica estadounidense, reconocida mundialmente por su trabajo en la formación y evolución de galaxias. Los astrofísicos ya lo son. Es profesora de la Universidad de California en Santa Cruz y personal del Observatorio de Lick. A lo largo de su carrera realizó descubrimientos fundamentales sobre la estructura de las galaxias, como los que ligan el brillo de las galaxias con la velocidad de las estrellas que las componen, la relación Faber-Jackson, lo que en los libros de texto especializados se llama relación Faber-Jackson. Entre otros importantes descubrimientos, como otras relaciones de proporcionalidad de las galaxias, sus contribuciones sobre la naturaleza de la materia oscura en las galaxias o la importancia de los hoyos negros y su papel regulador en la evolución de las galaxias. Esto quizá ya no lo sepan, ¿no? Los de astrofísica, el resto probablemente tampoco, pero Sandy fue instrumental en el diagnóstico de la aberración óptica que tuvo el telescopio espacial Hubble en sus primeros años. Era una aberración no de diseño, sino de fabricación, pero el cómo componerla y el qué era lo que pasaba se debió a un grupo de 3 astrofísicos, entre los cuales estaba Sandra Faber. También es instrumental en crear el caso científico de los telescopios Keck de 10 metros de la isla de Hawái. Técnicamente no son los más grandes, pero realmente fueron los primeros grandes en funcionamiento. Y hoy en día encabeza consorcios de cientos de investigadores, como por ejemplo el consorcio CANDAS, que es importantísimo para la formación y evolución de galaxias. Huelga decir que ha recibido los más grandes reconocimientos del mundo de la astrofísica. Y solo voy a mencionar algunos. Entre una larga lista, vamos a destacar la medalla Cruz de la Sociedad Astronómica del Pacífico en 2012, el premio Russell de la Sociedad Astronómica Americana por una vida de contribuciones a la astronomía. La Medalla Nacional de la Ciencia, impuesta por el presidente Obama en 2013, este es el reconocimiento científico más importante de Estados Unidos. Y está en la fotografía del cartel que han podido ver, seguramente. Y el premio Gruber de Cosmología de la Fundación Gruber y la Unión Astronómica Internacional. Es un reconocimiento a nivel mundial. Y en meses próximos recibirá el premio Magallanes de la Sociedad Filosófica Americana. Y yo sé que a Sandy no le gusta que lean todos sus logros, quiere hacer introducciones cortas. Realmente esto es una minimísima parte de todo lo que viene en la semblanza completa de Sandy Faber. Pero se quedan con la idea de que tenemos un honor realmente en tener en esta casa a Sandy, alguien que realmente ha colaborado fuertemente con astrónomos mexicanos a lo largo del tiempo y siempre ha tenido un gran interés en venir a visitarnos y venir a visitar el gran telescopio ellíptico, cosa que haremos mañana. Thank you, Sandy, for coming here, and welcome. And now I give you your turn to speak.
Thank you very much. I guess it was a lovely introduction. So wonderful to be here. Just letting you know that from the standpoint of an astronomer of my generation, Holland-Zinkler Observatory is a very, very well-known name. And as I was going through undergraduate and graduate school, I was just reading all kinds of fundamental papers that came out of this place. And I've never been here before, so it's a great pleasure for me to visit you all today and give this talk. So I've been thinking, I give a little background here. I'm our co-PI along with Harry Ferguson on something called the Candles Project, which was a project with the Hubble Space Telescope to take lots of deep pictures in 5 different fields and study galaxies farther and farther away back in time. And so I've kind of been processing that information, and it has persuaded me that actually galaxy evolution is simpler than I thought previous to our work on candles. And it's inspired me to see if we can understand the properties of the candles galaxies as deriving in the simplest, most elementary way from the properties of dark halos in the universe, the dark matter halos, which I'll be saying a little bit more about later in my talk. And we achieved some success with that, and I'm taking the fruits of that model now and trying to derive the properties of black holes that would be in those galaxies. In other words, making a connection between dark halos, the galaxies inside them, and the black holes inside the galaxies. And then plucking out of the air the simplest possible justification that you would use for how a black hole beating against its halo might quench star formation in galaxies. So that's an overview of my whole talk. I put an outline here, but I just told you that, so I think I'll just skip over that slide. And plunge in first, especially for the people here who might not be that familiar with the evidence that we have in astronomy that we have black holes. So this is one of the great achievements of Hubble and later other measurements that have been going on. This is a Hubble image of the biggest galaxy in the Virgo cluster, M87, a famous radio galaxy. And it has been known for a long time, even from the ground, that there's this funny feature here sticking out of the center of the galaxy, something called a jet. And with Hubble, we can enlarge that and see the jet in more detail. And when we observe the jet at other wavelengths, we see that it's actually emitting X-rays, and it's also emitting radio waves. And so our picture for the jet is that it's a cloud of gas threaded with magnetic fields and very energetic particles that's been ejected from the center of the galaxy by, we all thought, a black hole there. And here is a picture of M87 and the radio wave. And the picture that we've been looking at up to now is this size. So I want to impress you with the fact that the total extent of the impact of the jet on this cluster, the Virgo cluster where this galaxy is located, is much huger than you saw in that tiny little picture before. And this is the radio picture. An X-ray picture with Chandra has been taken and looks much the same. So this radiation is non-thermal, and it's radiated by synchrotron radiation, very energetic electrons doing cyclotron or synchrotron orbits in the magnetic field, and at the same time able to emit not only the radio radiation, but by inverse Compton upscaling X-rays. Now, M87 is not alone. We can look at other galaxies at the centers of clusters. This is the famous radio galaxy Hercules A. What you see here is a Hubble image at the center, and then superimposed on that, radio lobes. And here's another example of a galaxy, famous object called Centaurus A. In the optical, it looks like a funny elliptical with a dust lane. We hypothesized that it's an elliptical that just ate a spiral with gas and dust in it, and the disk reformed and is orbiting the center of the galaxy. And when we look in the radio, we see the familiar double lobes, and in X-ray, you see this image. One lobe is brighter than the other, much brighter than the other. So what I'm trying to convey to you is that there's all this active energetic activity going on in these spheroidal elliptical-like galaxies. And for a long time, there's been a model that these jets have been created by an accretion disk. Here is the black hole. Now we're very, very close to the center of the galaxy. We're looking at something on the order of a solar system in size here. And gas falls in, it forms an accretion disk. The material gradually loses energy, accretes onto the black hole, and somewhat of a miracle occurs, probably having something to do with magnetic fields that are threading this material. Some of the material is expelled in a jet. And parenthetically, jets are everywhere in astronomy, even young forming stars make them. So if we don't have a complete theory, we shouldn't be too troubled. It lists as though nature has no trouble making these jets. So when we look at the surrounding of these elliptical galaxies and clusters, we can see that actually there's energy and momentum coming out of the black hole in the form of these relativistic plasmas. Here is yet another one of these galaxies called Hydra A. The whole cluster is suffused with a sea of hot gas that's radiating in X-rays, and the jet is going this way, and it's drilling a hole and actually excavating cavities on opposite sides of the galaxy. In yet another galaxy, there's an elliptical here, but we're looking at the X-rays. The X-ray gas, something slightly different seems to be going on. There are bursts of some sort, perhaps a little bit less energetic, that are also excavating cavities, but on a smaller scale in the X-ray gas. So we have multiple evidence from things like this that these black holes can have an effect on their environment by sending out relativistic clouds of relativistic electrons and magnetic fields. Now, the kind of object that I've been talking about up to now is a massive elliptical galaxy, often at the center of a cluster of galaxies. And the astronomers here know quite well that there are two kinds of galaxies, and one is called a spiral, a rotating disk of gas still making stars. Don't forget that, that's going to turn out to be important. And the kind of object that we've been talking about, these massive quasi. You might be wondering whether or not this circumstantial evidence for black holes and their activity is confined just to the elliptical galaxies. And the answer is no. We can see signs of black hole activity in spirals, although of a different kind. Hubble again comes to the rescue by taking very beautiful pictures at high resolution of the centers of what are now nearby spiral galaxies. And we see signs of some sort of eruption here going on to a double lobe here. These objects are called Seyfert galaxies. And the estimate is that a local galaxy of normal mass, a few times 10 to the 10th solar masses, would be in this phase, the Seyfert phase, a few percent of the time. Here's another example. So something's happening here. So yes, we see evidence of black holes, activity in spirals, but not these gigantic radio jets that we see in the elliptic. Now, our galaxy has a black hole. And thanks to work by Andrea Ghez and her team at UCLA, also, help me. Reinhard Genzel, right. Those two teams have been monitoring with the help of adaptive optics the motions of stars near the very center of the galaxy. And for going on almost 20 years now, and you just looked at this little movie showing how the stars move, and it's individual stars moving in a gravitational field that is dominated by a mass that's right there, so it's very easy to measure the mass, and it's about 4 million solar masses. So via dynamical evidence and other forms of observation, we put together a simple story in which basically all massive galaxies have black holes at their centers. And when the galaxy is small, it has a small black hole. When it's big, it has a big black hole. And a little bit more precisely, if the galaxy has a small spheroidal stellar component, that's what the mass of the black hole scales with. Okay, so keep that in mind. We're going to come back to this figure shortly. I hope I've convinced you that there are lots of black holes everywhere, and we know something about them. In particular, we know the scaling law, which is very important. Now I'd like to switch gears and talk about the model that I want to explain to you and where it comes from. So this model, as I alluded to before, is based on the fact that most of the matter in the universe is dark matter. And we understand the density irregularities of this dark matter. It's a key point. First of all, we have some theory for that. These density fluctuations that seed the existence of galaxies today were generated in the universe during inflation, which was at a very early time, 10 to minus 35 seconds. So how could we possibly believe that? How could we possibly have any physics that would be reliable at such an early time? Well, fortunately, those fluctuations, after they were formed, they did evolve in a rather simple way for quite a while, for about 400,000 years after the Big Bang. And they left their imprint on the cosmic microwave background. And there are fluctuations on our picture of the sphere. Typically, the microwave background has measles that are about the size of the moon. There's a peak there of 0.5 degree. And we can calculate what the size distribution of those peaks should look like, and we get amazing agreement. So from that, we really think we know what the origin of these fluctuations was at 10 to the minus 35 seconds, how they grew up to the time when the microwave background was in place. And from that time on, it's fairly easy to calculate how they're going to create galaxies. So a number of people have done this. And I'm going to start with this, this video, which shows just the clustering of the dark matter. The dark matter is about 75% or 80% of all the mass. And so it's doing most of the work in making objects. Let's see if I can find this here. This is the Milky Way. This is the volume which is supposed to represent our galaxy. And so the first thing you note and there are big blobs. They grow at different rates. They tend to merge in a hierarchical process. And in the vicinity of a galaxy, they tend to coagulate and create a center, which is a potential well, which is now going to accrete ordinary matter into it. Second thing you notice from this picture is that the dark matter creates structure which is rather ropey looking. They're called filaments. And that structure is more or less the same on every scale. We're looking at a picture of dark matter clustering inside a galaxy. But if we looked on the scale that's 100 times bigger, it would, the topology of the clustering would be quite similar. Okay, so here's the net result. There is a halo. There's a tiny galaxy at the middle. That galaxy has much less mass than the total halo, and it's physically a lot smaller. So why is that? Let's just pause for a second. That's because the physics of the ordinary matter, astronomers say baryonic, that's the matter of this room, our planet, the periodic table. Its physics is different from the dark matter. The dark matter clusters but cannot radiate away any of its energy, whereas the clouds of baryons, when they collide with one another in the process of falling into this potential, they heat up, they lose energy, and they fall to the center. So the net result is that galaxies are in these two different pieces with the baryons at the middle, surrounded by a much bigger and invisible dark matter halo. Okay, so what I want you to remember is that actually we really understand the dark matter very well. First of all, we understand its original density fluctuation spectrum, and because it only responds to gravity, we can calculate in a computer how those particles respond to all the other clumps of particles. So that is the scaffolding on which my little model is built, an understanding of the dark matter. Now let me just ask you to imagine the simplest possible scenario, which is that whenever I make a halo, the same percentage of baryons makes a galaxy. What would that look like in a plot like this? This is a plot of number density of objects versus the size of the object in mass, here, log of the mass. And this trajectory here, which I'll outline with a little activity, okay? That's the number density of halos in the universe, which, as I've said, we understand very well. So if galaxy masses always formed in proportion to halo masses, what we would expect is a plot that looks rather similar to this, maybe slightly depressed below, but with the same slope, because every one of those halos would be making the same kind of galaxy. And we don't see that. So we see a deficit of small galaxies relative to their halos, and a deficit of big galaxies relative to their halos. Now, the small scale problem is not a problem, because we know that when galaxies form and their stellar generations start taking off, star formation is intense, especially in the early universe, we have a lot of supernovae that can blow gas out of the galaxy and prevent further star formation. So that negative feedback can depress the numbers here below what we would expect. But that doesn't work at this high level here, because the energy of supernova feedback is not adequate to get gas out of the much deeper potential wells of the bigger halos. And so this has created a problem. And this is what makes us think that maybe first of all, we need to stop star formation, because if we kept on forming stars here, we'd expect a curve that would follow the halo curve, and it doesn't. So at high mass, star formation is being suppressed. We need to do that. Now, people have suggested basically two different ways of suppressing star formation. So I told you before that there were two kinds of galaxies, and it turns out that objects in which we're trying to suppress the star formation, the so-called elliptical galaxies. Now, it's very important to know that these ellipticals are not ancient, not all of them anyway. This is not what we thought 20 years ago. There was a theory that ellipticals were quenched way up at redshifts 2 or and we found that their numbers are continually increasing. In fact, their numbers have tripled since a redshift of 1, which is 8 billion years ago. The point I am trying to make is that the quenching process is long-lived. It might have started with some galaxies at quite early times, but it is now continuing today. Blue galaxies are turning into red galaxies, and we want to know why. Supernovae don't work, so let's not consider them. Two other points of view. One, which I helped to develop myself way back in 1984, is the idea that as time goes on and the halos get bigger and bigger, their characteristic orbital velocity inside them is increasing, and their characteristic density is going down. It's easy to derive this from clustering in the universe. Now, baryons are falling in. They collide. They collide at higher velocities in the bigger halos. Their orbital velocities are transformed into heat, higher temperatures in bigger halos, and at the same time, lower density. This means, in a very general way, that the bigger halo of gas has a harder time to cool. There's a cooling law that you can write down for hot gas. And when the gas gets hotter and less dense, it doesn't cool as well. And that's illustrated in actual simulations here. Here is a halo of 10 to the 11th solar masses. The blue gas is able to cool, and we see that there's a lot of mass falling onto the center of the galaxy. So that galaxy would be making stars. It would not be quenched. In contrast, here is a halo that's 100 times bigger. Its characteristic temperature is higher and its density is lower, and the computer simulations show the formation of a shock here. Infalling gas goes through the shock, and behind the shock the gas is hot, and so there would be, this halo would be harder to cool, and its galaxy at the center might be accreting much less. People have looked at this. It's definitely an important process, but by itself, it doesn't seem able to completely shut down the star formation that we need. So there's another point of view, and that is to invoke the role of AGNs. An AGN is an active galactic nucleus, and that's what a black hole does when it accretes. And people are now making models of this. They're putting AGN into galaxies that are forming. So this is a really beautiful simulation, the latest from the Illustrious team. And time is passing, but as the structure gets bigger, the camera steps back, so the expansion has been taken out, and that allows you to see the details inside. And so the first thing that we note are these ropey structures. That's what I alerted you to before. That's what dark matter does. That's what we expect. And the galaxies are forming where the filaments intersect. And now if you look very closely, you're not seeing stars in this video, we're seeing gas. And if you keep your eyes open, you'll see that there are explosions taking place. Let me see if I can see that. Ah, there's one in the back. There's a big one. I spotted all the early ones in the beginning of this video, and now we're reaching the end of it. There's another one, okay? So this simulation is the latest attempt by this group to actually try to model what an AGN might do and its ability to throw gas that already accumulated into a galaxy to eject it. This is an example of ejected feed. So they're busy analyzing these simulations here, and we don't have final results yet, but I've seen some early results. And let me now make a criticism of both of these points of view when used in isolation. Let me remind you, the first point of view was haloquenching, and the second point of view is AGN ejective feedback. Both, first of all, I told you that hot haloquenching doesn't seem to quite work all by itself. You need something in addition. But in addition, both of these mechanisms have a fault. And in my opinion, people are not pointing this out strongly enough. The fault is that both mechanisms tend to predict that galaxies will quench when their halos reach a certain stellar mass, and that means when their galaxies also reach a certain mass. In other words, there should sort of be a wall here. Everything below a certain mass, which is about 3 times 10 to the 5 solar masses, should be forming stars, and then suddenly, boom, everything above that would be quenched. And that's not what we see. So let me show you, this is where candles has had a big effect on me. Let me introduce this figure. This is candles data. And we have 4 panels here that are in different redshifts. The redshifts are shown here. So this would go back to when the universe is maybe 2.5 billion years old. And we come down to 4, 7, something like that. And this panel is the youngest. And the universe then, in that panel, will be maybe 8 or 9 billion years old. So we haven't looked down to the present. The present will be over here. But this is what candles can see well. So each of these graphs is a plot of galaxy radius versus the logarithm of the stellar mass. And this first plot shows you the star-forming galaxies only. And what you note is that aside from a few little stragglers here, which seem to disappear at 8 times, the star-forming galaxies lie above this red line. The red line is an empirical line. It's just been drawn to divide populations. Contrast that, here's the same graph now for the quenched galaxies in the same redshift ranges. I'll go back and forth so you can compare. So what we're seeing here is that quenched objects at a given mass here have a smaller radius. And if you thought, as you will see in a second, and see this is what I think, if you thought that galaxies were evolving through, maybe there's a boundary here such that when you reach it, your star formation actually stops. So actually that's the premise of the model I'm going to show you. So here is a dark halo-based model. We understand the halos, and we're going to base the properties of the galaxies and the black holes on those halos. So here are the assumptions. Every dark halo is assumed to host a central galaxy. This is a theory about central galaxies only. The astronomers recognize that there are other galaxies and clusters that we call satellites. They're kind of a separate phenomenon, and I'm not talking about them today. More massive galaxies are in more massive halos, and we have actually a rule for that called the stellar mass-halo mass relation, which is empirically measured. And now, this is new. So far it's not new. Next point is new. We're going to assume that the average galaxy radius while star forming is 2% of the halo radius. These radii have well-defined radii called virial radii. And the galaxy radius is going to be 2% of that. On average, for the average star-forming galaxy. But we're going to allow for the fact that there's some scatter, that a galaxy can either be above or below that. And furthermore, we're going to assume that that scatter, up or down, that offset is constant throughout the life of the galaxy. So these two things are new. And finally, we're going to assume that the black hole mass scales as central stellar density, this parameter sigma 1, to the 1.76 power. Sigma 1 is the projected stellar density within 1 kiloparsec of the center of the galaxy. And we have some empirical justification for believing that the black hole mass scales with the central properties of the galaxy. And I can discuss that later if you like. Okay, so now let's just imagine that we're looking at the results of this model. Because we know what the halos are doing as a function of time, we know what their mass is doing, what their radii are doing, we can now predict the stellar mass and the stellar radius of the galaxies, and the net result is that fairly high accurately, galaxies follow a power law in this plot of log radius versus log mass. But because we've assumed that there's some scatter, there's not one track here, there's parallel tracks. And so the interpretation would be that this object here has a particularly large radius compared to that one there, just because of the scatter. I can speak a little bit more about theories for the origin of the scatter, but right now I'm going to skip over that. I want to move now for the galaxies to the black holes. I remind you of this correlation that we saw a minute ago, and it turns out that we can rewrite this correlation, just as I said, by, instead of using bulge mass here, we'll use this parameter central sigma 1, the projected stellar mass within 1 kpc radius. Why can we do that? Because we can measure a good correlation between those parameters. So I'm going to substitute that. And now let's look At this plot, the threads of the logic are now beginning to come together. Same log radius, log mass plot, but now we're coloring the points by this central density parameter. And lines of constant sigma 1 are slanted in this diagram, so that this object here has high density, it's green, and that one there has low density, it's purple. And using the scaling law in the model, this 1.76 exponent, the difference in black hole mass is a factor of 17. So let's recapitulate. Galaxies have a large scatter in radius at a given mass. They have a large scatter in central density. Let's assume now that that corresponds to a large scatter in black hole mass. By the way, parenthetically for the astronomers, if this scaling laws are correct, you can actually just read off the black hole mass by knowing the stellar mass of the galaxy and its effective radius. In other words, this plot, which is very familiar to us, is actually a map of black hole mass. So powerful in other ways. Okay. We have the galaxies evolving on parallel tracks. And now let's just, out of the blue, assume that there is a quenching boundary, and we're going to put it in here in a way that is tilted. So the consequences of that will be, if you work up them all, that these objects here, which start out with small black holes, need to evolve to larger mass in order to get a black hole quenching quotient that equals the quenching power of the dense galaxies, which have big black holes. In other words, these guys here are sort of retarded, and these are advanced in this picture. So the one thing that remains now is to figure out whether or not there's a theory that would justify that tilted boundary. So let's talk about that. That's obviously a very important point. And here in this little model is the physical definition of the quenching boundary. As black holes form, they are believed to radiate a certain fraction of their rest mass in the form of energy that gets out. And I'm going to assume that the fraction of that rest mass energy that could do some work on the halo, but have an effect, is 10%, which is kind of similar to what other models assume. So this is the total energy that's been radiated by a black hole when it's attained a mass of MPH here. Now, what are we going to do with that energy? In this simple model, we're going to say, here's some energy from the black hole. Here, it's sitting in a halo that's full of gas. We want to either disable that gas or get rid of that gas. We want to make it impossible for that gas to fall on a galaxy. Well, order of magnitude, what kind of energy do we have to put into that halo to make that happen? The answer is order of magnitude equal to the binding energy of the gas in the halo. And what is that? That's a half times the mass of the gas times the typical orbital speed of a gas particle inside the halo, or alternatively, something in the region of KT, the temperature of that gas. So our little simple prescription here is that we're going to set the energy of the black hole equal to this energy here, and if it all were, there was no cooling, no loss, or anything like that, that would be the amount of gas that could just unbind, the amount of black hole mass that could just unbind the halo. That would certainly stop quenching. So what's the result? We can work through all the math in more detail, and we can predict the location of that law in the diagram that I just showed you. I showed you the red lines before, which were the empirical divisions between the star forming and the quenched galaxies, and now overplotted the blue lines, which is the theory that I just gave you. So, let me skip back and forth. We were just looking at star-forming galaxies there. And here are the quenched galaxies. Go back and forth a couple times.
Yeah, well,
Okay. It does.
the gray,
Yeah.
yeah, they become gray.
That's right.
Oh, I see.
Yeah. Okay, it's a little different from the first one.
Roberto does it.
Right.
So they become a little bit larger.
Okay. Okay, so what do we see from this? First of all, you know, there's been no adjustment constants here to make things fit. The only thing that was adjusted was the 10%. And I just took the binding energy and stuck it in, and yet, remarkably, overall, there's good 0-point accuracy. That's encouraging. It could be a fluke, because I think the efficiency of this process is a little unknown. More interesting to me is the slope. I argued that nobody else, no other theory, had reproduced the fact that there was a range in masses here, and I should have stressed that no other theory has reproduced the slope either. And yet the slope is closely matched with this single theory. And finally, a point which I have not had a chance to emphasize in this brief version of the talk, this red line actually changes its 0 point. From here to today, it marches down by 0.3 of a dex. And I think the most outstanding good thing about this halo cooling or halo quenching picture is the fact that very naturally the properties of the halos are keeping pace, and they are also falling by 0.3 of a dex. So this is encouraging. Now I'm going to end with some ridiculously speculative thoughts. I emphasized before that we can see the feedback into the halos when we look at these big ellipticals. But I also stress that we can't see nearly so clearly the feedback from the spirals. So what are they doing, you know? Is anything happening? Here's a ridiculous idea. Our galaxy has something called Fermi bubbles. And these things were discovered with a gamma ray satellite. They're also seen weakly in X-rays and radio, but they're extremely hard to see. We're doing calculations and think that they could not be visible with present technology in any other, even nearby galaxy. People have looked at Andromeda and cannot see a clear signature of a Fermi bubble. What is this thing? It's an inflating hot globe. It's slightly overpressured. It's about twice the pressure in here as against the hot gas in the surrounding halo. It's expanding. You can calculate its expansion time. It's a few million years. That corresponds to previous events that we can date in the activity of the black hole at the center of the galaxy. Maybe it's made clearer by this cartoon. Things are always clarified by cartoons. Right, so here we are out here. This thing is huge. And it's long-lived. Even though an event dies down in the center of the galaxy, you can calculate the cooling time inside these lobes. It's long, it's 100 million years. It's much longer than the time between the events of the hole itself. And so it's plausible that you generate this thing and you just keep on inflating it with every new event that you make. So the important thing is two important things. First of all, how much energy does it take to do this? And can you do it with a simple starburst, or do you really need to energize the black hole? There's controversy in this. This paper here says that you cannot do it with a starburst and you need an AGN, but other people disagree. So this is an open issue. However, very interesting is the fact that this thing is overpressured. And that means that unless you have a bullet of gas going down through it, if you have something smooth with lower momentum per unit area, it's going to be deflected. So as long as we have these Fermi bubbles in our galaxy, again, I'm being speculative, these is an umbrella that that might be shielding the inner parts. And this is how we see galaxies going out today. All big galaxies go out in the middles. This is a double picture of M31, which is exhibiting this. It has a red and dead bulge and a ring of young stars. This is the red light from the old stars. And so maybe M31 has its own Fermi bubble, and its middle is being shielded, and only the outer parts can still accrete gas. Okay, so I will now give you some summary. First of all, the scatter and the radius of the galaxy was the key. That was what gave us a variation of fixed mass in the black hole mass. So independently of whether any of this is correct, I urge us all to think of galaxies as a two-parameter family, at least while they're star forming. Not only the mass, which is what people generally tend to think about, but also the radius. There's a big difference in the property of these big galaxies compared to the compact ones. Okay, maybe the radius offset is constant while the galaxy is star forming. The model needs that to be true. That would say that galaxies that are big today have always been big, and galaxies that are small today have always been small, relatively. And that might have big consequences for their evolution. Galaxies build black holes as the central density while they are star forming. That's a very important point. They don't, in this model, they do not build in a certain burst. There's not a mass at which you suddenly create a hole. They're gradually building over time. And early measurements of X-ray activity in galaxies of different mass are tending to confirm this more gradual growth. I said this before now, you can read the black hole mass off from simple location, effective radius versus mass. Okay, the last 2 points are about the quenching. It's not just AGN quenching, and it's not just halo quenching. It comes from balancing the AGN versus the halo. So it incorporates both points of view, marries them, and puts them together. And you saw that those plots versus redshift look the same at all redshift. The same tilt, just this gradual drift and 0 point, which is predicted by the halo properties. So we would conclude from this that the same basic physics is governing quenching in all redshifts. And this is a new thought. It's different from what people are putting into their black hole halo quenching models. What people are now putting in is quenching when the rate of the black hole growth equals the cooling rate of the halo. We tried that. Doesn't give the right time behavior whatsoever. This is really new. This is a total black hole mass, not a rate of accretion. And this is a total halo binding energy. And I think that really is what is required to make this whole picture work. So I'll stop there, and thank you very much.
I don't know how this works. So, time for questions.
Maybe we can turn the lights on.
Ya. ¿Pueden poner las luces?
Sí, ya, sí.
¿Pueden conectar las luces, por favor? Preguntas, Sergei. Juan, ¿tenemos otro micrófono?
You mentioned.
Okay, thank you very much. Nice talk. You mentioned that galaxy sizes scales with dark matter rate. How one can measure the dark matter the radius of the dark matter?
Well, in an individual galaxy, you cannot do that. But I'm making a model which applies to families of galaxies. So I just need to predict, on average, what galaxies will do. And from clustering theory, we know how galaxies change their mass and radii, halos change their mass and radii as a function of time. That's really, your question is going to the heart of my basic assumption that we understand dark matter.
And another question, if you allow me. How star formation, affects this accretion processes? On one of the first slides, you showed examples of spiral galaxies and elliptical galaxies with a central black hole. And in particular, in spiral galaxies, the image of the galaxy which you showed with these filaments of the gas which came from the central part of the galaxy, it is very similar to what we are observing in M82, typical star-mass galaxies. So, how to distinguish in both processes black hole activity and star formation? They require high gas densities, because high gas densities is required to form stars, but also the black hole luminosity depends on the mass accretion rate, which also depends on the gas mass. So what is the relation between the two, this negative feedback taking, the black hole activity and the star formation activity? And how can you be sure that in this particular case of the galaxy that you showed us, that this is black hole feedback, but not star formation, central star loss feedback?
I didn't mean to read as much into those pictures as you are. All I wanted to do was to indicate that there was special activity going on at the centers of galaxies, which many people interpret as black hole activity. Now, I think what you said is a very, very good point. If all I'm doing is looking at a picture of one galaxy, I might have a very hard time telling the behavior of the kinematics of the gas and the morphology of the filaments, distinguishing between a black hole-driven process and a star formation-driven process. And you mentioned M82, which is a classic example of that. That's a star formation-driven wind, not a black hole-driven wind. But those were just a couple of pictures. We have measured black hole masses in the centers of many spiral galaxies using a variety of different methods. And so we know that the spirals basically follow the same sorts of scaling laws as the bigger galaxies. And those are dynamical measurements. They also use masers, a variety of different techniques. So I think there's just no question that spirals contain black holes at their centers. In general, they're smaller than the black holes in the big universe.
More questions? Monica?
So how do you create the scatter in the radius?
Yeah, so that's a difficult issue. Until recently, people were quite comfortable with the picture in which you could have two dark halos of different mass, but different net angular momentum. And more rapidly rotating one would create a bigger galaxy. Okay? That's being called into question on the basis of models. So to the extent that one believes models for galaxy formation, the models don't say that that is actually happening. And 3 sets of models have now been looked at, and 0 correlation has been found between the delta angular momentum of a halo and the delta radius of the galaxy that forms inside it. So people are now looking at another parameter, and I'm a co-author on a paper with Feng-Chu Zhang, who is looking at halo concentration. So the way to do that is to look at a simulation like NIHA, for example, which has simulated star halos and separately has simulated the halos with the galaxies. So you can look at the concentration of the halos as they were free of baryons. And the theory seems to be working out very well in that set of models, that when you have a higher concentration halo, you make a smaller galaxy. So that is our best working hypothesis for the radius difference.
Thank you. I have a question related to the correlation between the black hole mass and Bush mass. So,
What is that? Black hole mass and,
the Bush mass, the correlation you show.
okay.
So the question is about the pseudo Bush. We know this pseudo Bush also follow Faber-Jackson relation. They populate the low part. So the question, how do they fit in this correlation?
In general, you can test my formula. Black hole mass equals sigma 1 to the 1.76. Sigma 1 turns out to be also expressible, as you would have guessed, as a function of stellar mass and radius. And so there's an equivalent formula, which I showed on the slide, I went over quickly. Okay, so that's a family of measurements, black hole measurements, galaxy radii, galaxy mass. The model assumes a certain set of exponents in there. Separately, we've measured black hole masses for galaxies of radii and masses. Does it agree? And broadly, it agrees in the sense that the measurements say that black hole mass should be a function not only of stellar mass, but also radius, and black holes should be smaller in galaxies with bigger radii. So that's good. In detail, the value of the exponent that we need, seems to me, is too low. So instead of 1.76, the data would really like to have more like 2.1, 2.2, something like that. So at that level, there's a disagreement, but since this is just a toy model, maybe we should take comfort in the fact that the measurements are suggesting general trend that we need. The paper that you would want to look at is by Remco van der Bosch.
Yes, thank you very much for this nice talk. I really liked the idea of the Fermi bubbles that you presented, and I have two questions related to it. So, if they are producing some kind of shielding for the nucleus, for the bulge, then do you expect them to be in all separate galaxies?
Mm-hmm.
All of them should be
Not just separate galaxies.
or any galaxy?
Any spiral.
Any spiral. I mean, I wanted to say spiral, not separate, actually. And so what is the requirement for a galaxy to grow or to inflate a Fermi bubble? How are they formed?
Well, people make various models for our Fermi bubbles. Some people inflate them through star formation. Other people inflate them by injecting relativistic plasma jets. So I obviously am in the second camp. I want the black hole to do it. And it's been remarkably difficult to tell the difference between those two approaches.
Annalisa, could you please back to the slides 4?
Could you go back to slide 4?
Oh, okay.
Number 4?
Yes, I think something like this.
What did it contain?
What did it contain?
The orbits.
The stars around the black hole. Yes.
How do I get back? Is there a quick way? Do I have to get out of President? Nobody's ever asked me to do that.
Okay.
How do I get out? Oh, escape.
Escape.
Okay. And,
Yes.
okay. Okay. You want it animated, or do you just want to look at it?
Only this.
Okay.
We know that the direct method for estimating black holes is with the velocity of the stars around the black hole, right? When the star finish.
I actually hear that. Say that again, please.
Okay, when the star finish the orbit around the black hole, we know the mass of this black hole.
Yeah.
Is the direct method.
Mm-hmm.
But thinking around the relativity, general relativity, we know that the orbit is not closed, like a Mercury perihelion.
Mm-hmm.
And so, how this affect the determination of the black hole mass?
Yeah. So the people are working very hard now just to detect that effect. And I'm not sure that it has been detected. Maybe somebody else in the audience knows. Has not been. But I know that both groups are working hard to see if they can see it. So at the level of just estimating the black hole mass, it's not important. It's secondary or tertiary effect. It's very small. I think what you were asking is, do we need a general relativistic correction to the black hole mass? And the answer is no. At the level we're working here.
Can I ask you about those festering star-forming galaxies in the Quench galaxy region?
Sure.
So what is your best bet for why we deviate from the general scaling?
These guys.
Yeah, that's right.
Right. I don't fully understand them.
I mean, it's a very nice picture. I mean, it really represents most of them.
Yeah.
But there are so many of them. I mean, there are a few of them,
Actually,
especially at high redshift.
this doesn't show them quite so clearly.
The previous one.
Cleaner diagram. This one.
Yeah. Especially at redshift 2.
Yes. Okay. So again, the astronomers will recognize these. These are the interlopers. These are the nonconformists. Right. These are the so-called blue nuggets. Do you recognize that?
Yeah, yeah.
Right. So they were a major, major discovery in the last 5 years or so. So they give rise at the same redshift to quenched galaxies. And detailed study of this one is star forming, true, right? But when we count their number versus time, the star forming ones are disappearing, right? Or at least moving to lower masses. Whereas the number of quenched galaxies is increasing. And the thought is that these are very, very small, very, very dense, and will later accrete the more bloated, diffuse envelopes that are required to make them into giant ellipticals. And people, we have a paper on this, estimate their evolutionary track in this diagram as a function of time. It's very steep, so these guys are going like this. Their radius is varying as the mass squared.
Is there evidence that they have black holes?
They're X-ray sources. Yeah. So I think the question is, my toy model is very conservative. It says a lot about what things are doing in here. And big question mark right there. What happens when I cross the boundary? How do I evolve further? And I think that story changes as a function of redshift, primarily because of this diagram. So when I cross this boundary here, I'm full of gas. And models at that time, Abishai Deckel's become famous for this kind of model, has advocated a compactification process, which actually might drive the black hole mass and encourage quenching. So these are a temporary state of how galaxies quench when they're star forming at high redshift. At today's redshift, they don't do that anymore. The Milky Way is not going to turn into something that's 2 kiloparsecs wide. So the actual post-crossing physics is dependent probably on gas content. And I think it's fascinating. I don't yet try to model it.
Yes, please.
Okay, the other way around.
Okay, this is really a quick question. About the simulations, you present how the universe was evolving, the black matter with the baryonic matter. So I want to know if this simulation is used for visualization or it is giving us scientific data. Or could you explain us a little more about?
First of all, there are many simulations. Is it the one that I showed, the illustrious simulation?
It was the first one. The first one or the second one?
The dark matter only simulation.
Yes. How is the dark matter evolving with the baryonic matter?
Okay. What's your question about it?
I want to know if this simulation is giving us real scientific data or this is just for visualization.
I think it's a real simulation.
It's real simulation.
It's a real simulation.
Yeah. It's the first of its kind to show dark matter at high resolution in a galaxy. Remember, that was the Milky Way.
Okay. So, is there any page where I can find the link for the simulation, or just to know a little bit more about it?
Why don't you speak to me after the talk, because all of that work has been published. The author's first name is Dieman, D-I-E-N-A-N-D, with Maddow, and if you look those papers up, it's all been published.
Okay, thank you for your nice talk. I want to know something about the sizes of the radio lobes, because you showed at first that some radio galaxies have these large lobes, but there are also evidences of giant radio galaxies which are in the scales of megaparsecs, right? So do you think that the halo, the scale of the halo, even in mass or radius, could affect that these radio galaxies could reach these giant scales?
Again, those pictures were supposed to be illustrative and convince you that black holes can do big things. The model for the radio source and the lobes is not in my picture. I'm just using them as evidence that black holes can send energy into halos. I know that there's been a huge amount of work trying to figure out what the sizes of radio lobes is as a function of cluster mass, redshift, and stuff like that. But I could not, for the life of me, summarize one conclusion from any of that. So I'll just have to pass on that question. It's an active area of work, though. Do you work in that area?
No. I work for.
Okay. We're going to cut the question time now, and just going to advertise, especially for the students from astrophysics that are going to have lunch with Sandy, and we are going to have coffee for any researchers that are interested at 4 p.m. in astrophysics, and people from other coordinations are, of course, invited to join us. So let's thank Sandy, and I think...
Thank you.
La doctora general le dará un reconocimiento a la doctora Sandra Faber. Ahora tenemos un brindis en honor de la doctora para quienes gusten acompañarnos.
¿Ya apagamos la cámara? Ya está. Lo apagamos.
Sí, si quieres venir al centro también puedes venir al centro. De aquí, algunas
Se desconectará la llamada.